thank you for the invitation. For participants which maybe are online, so we are sorry for all the technical problems today, which of course necessitate to adapt the schedule. So this is my first talk of the day, and my second talk will be in the afternoon. In fact, the slides. Oh, no kidding. Oh, really? Okay, that's not good. Yeah, so the slides that you will find here are supposed to be my first two lectures, and there will be a new set for the rest, more or less. And by the way, you will find also on this website a list of reference. So it's just a text. And so each time that you see a reference within bracket, it means that you have to look back to those reference. And I will add a further reference. Okay. So, in some sense, my first lecture, the goal is really to glue together several aspects of cohomology of groups, topological aspects, which have been discussed during the past weeks and during the lecture of Paul, Peter, and Jean. And so you will see connections between the different point of view, and also to introduce K-theory, as it was mentioned by Paul earlier, and theory. The goal is not to understand deeply what is exactly K-theory, but it's more to get the object as a black box. So there will be numerous black boxes. Okay, and this is the goal. The goal is to be able to use the black box without knowing exactly what you have inside the black box. It is the purpose of a black box, by the way. Okay. On the other hand, on the other lectures, I will go deeper in the details. So I will explain what is really going on, either from a mathematical point of view or from a computational point of view with mainly Voronoi complexes, for instance. So, and as for the last lecture will be dedicated to some problems and challenge, big and small, meaning that some problems are really hard problems, but I will also mention problems which are very easy to grasp and to enter into the game. Okay. No kidding. So our first player is K-theory, meaning algebraic K-theory. I did not speak at all about topological K-theory of its variant for operator K-theory or KK theory. Even it's connected, but it's really another story. So I do not want also to give the historical background on why we needed to consider those groups. So it's an infinite family of abelian groups parameterized by the natural numbers that you can add to, let's say, a ring or a scheme. For our purpose, assume that the ring is commutative, but the constructions that I will explain in a few minutes is of course available for abstract ring commutative or not, schemes, and even categories. Okay. You can use it for fancier and abstract structures, and it is also useful. So at the start, we had several, let's say, groups. So usually these groups are denoted K for classes, for the German name class. Even if I say that I won't give a historical lesson on this, nevertheless, there are some historical landmarks. The story started with the initial group, what we denoted K naught, and which was, let's say, introduced by Grothendieck, which, well, classify vector bundles of finite rank in the geometric setting, say, or finitely generated R modules. So it depends if you look more on the algebraic side or on the geometric side. Then Bass introduced another group which was connected with a short exact sequence to this group. And so for this reason, it named it K1. And in the case where R is a commutative ring, it is very easy to describe because it is just the inversible of R. So if R is not commutative, you need to obstruction. Then later, well, let's say Milnor introduced another group which classifies the universal extension of SLR. And it turns out that it gives also a nice functor. And again, with a short exact sequence relying K2, I mean, this new group to K1 and to K0. So of course, it called it K2. And moreover, more surprising, he was able to give a very nice presentation by generator and relation for this group. And using this only this part, the description in terms of generator and relation, it gives rise to what we call later the Milnor theory. And so in the case of K2, assuming some hypothesis on R, both coincide. Okay. And in some sense, this was the beginning of the story. Yes?
I just wanted to add projective to K0, the word projective.
Yes, finitely generative R module. Yeah, you're right. But very soon they are going to be free, so. But yeah, you're right. Yeah. So yeah, you're right. So it's projective R module which corresponds to the vector bundle. Yes. And of course, at some point, so in the 70s and early 80s, even already in the 70s, the goal was to construct a general family of K groups, which fits in all this, let's say, low-level scenario for this. Oh, this is rather annoying. Sorry. Okay, so this was provided by Dan Quillen in the 70s. And I mean, it was also part of his field medals. And strictly speaking, it provided two constructions for this. One very topological and in some sense very easy to consider, which is the so-called the plus construction, but of course, which is lacking, I mean, it's difficult to grasp K0 with this construction, and which is lacking some nice piece, nice machinery behind it, because in part it was not categorical. And then, a few years later, propose a categorical construction called the Q construction. And this one was in some sense a good one, I mean the one for which we can easily work, and we have plenty of very nice machinery that we can use, and in particular we can use it in both for, let's say, an algebraic setting or a more geometric setting if you use scheme or algebraic, K-algebraic varieties, for instance. So in fact, you can have in mind as fundamental example Z. I mean, R equals Z, or eventually R equals, let's say, a number rings, but mainly even a number ring which is a PID. Okay. So we define Q as well, mainly, I mean, the category. Well, it is more than that. Okay, but mainly it is made of 3 R modules of finite rank. And Qn is the filtration, in some sense, of this category by module of rank at most n. Then we can take the classifying space of the category, and corresponding in some sense of the geometric realization of the category. And you define the K groups, the M K groups, as the M+1 fundamental group of BQR. And then it is already not so to prove that K0 is indeed P1 of BQ, that K1 is indeed P2 of BQ, and that the K2 that I just loosely defined is P3 of BQ. Okay. So, and in the remaining, in the case where R is just Z, I will just denote it by Q and Qn. So I will drop the Z. So there are several ways to construct those groups. So as I said, so there is a famous plus construction that I will just describe again loosely as a black box in a few seconds. But there are more topological construction using the, let's say, more spectra description of the K-theory. Then you can build, let's say, again, a categorical structure on it. And it's more or less what proposed Waldhausen, for instance. And then you have really a very different way to construct it, more or less more algebraic. At some point, you always need topology and homotopy to enter the game, in particular if you want to prove that all the different constructions. And all those constructions turns out to be very useful, because depending of your problem and what you need to prove, some constructions are easier and give you machine, and other construction will give you another type of machinery. As you can see, I am very careful not saying that the construction gives you an explicit way to describe elements, because none of them could, except for the Miller K-theory. But this one is only a piece of the algebraic K-theory. And it's also why it is related to the polylogarithm and what we call block groups, because it also in a way, in the case of fields, to give a presentation by generator relation of the K-theory in the case of. But in general, it is very, first, it is very difficult to compute this group. And it is even more difficult to give explicit elements of the group. And what is very frustrating, as you will see in a few minutes, on the other hand, we can claim precisely that there exists some specific element for a given torsion in some given K groups. Okay? So we are sure that they exist, but we cannot construct them. Okay, so in the exercise session of Peter, so it was discussed the stabilization morphism of for GL. But of course, if you have this for GL, you have this for all matrix groups, and in fact, strictly speaking, you have it also for permutation groups. Okay. So what we consider for this, we need to consider what we call the full general linear group, or the stable one, which, let's say in modern language, is the colimit of the stabilization morphism. Okay, so you just, the map is given by this. And so the colimit of this will be this guy. So you think of this guy as the reunion of all the small guys. And you have a way to identify elements between GLN and GLN plus 1, GLN plus 2, and so on. Okay. So if you pick an element in this, it is always finite somehow. Okay? So at some point, you will just have 1, 1, 1, 1, 1 up to infinity. But the core of the guy will be in some GLM for M big enough. And it goes the same way for SL, as I said, and all the groups. In fact, it also works for covers of those groups, as, for instance, a Steinberg group, for instance, that you can see as a cover. So the idea of the plus construction is simple in its principle, not necessarily so difficult from a topological point of view, but it's simple. You take the classifying group, the classifying space associated to a group, the ones that you already have seen during the first week. And as you know, the fundamental group of the classifying space will be the group G. And you wonder how it could be possible functorially to modify the space in order to get an abelian group, but in some sense in almost canonical way, which will be abelianization of the group G. Okay. And this is why the plus here. The plus means abelianization. And so it's, in some sense, it's just a way to killing commutators, if you prefer. And killing commutators is something that you do topologically speaking at the level of the space. In some sense, it's just, let's say, removing holes by adding cells of correct dimension. And this plus construction, which was first proposed by Quillen, has plenty of nice functionality, but unfortunately not as a full machinery. Of course, if you want to do this for schemes, it will be a little bit more difficult. If you compare it with the Q construction that we just described a few minutes ago, it turns out that, in fact, the plus construction of GLR is the loop space of the Q construction. Okay. So it means that you have a shifting by 1 at the level of the homotopy group. Okay. And why this point of view is interesting is because you get an immediate connection with the homology of GLR. Because another property of this construction is that, okay, you abelianize space somehow, but without changing its homology. And so the homology, meaning the singular homology of BGLR plus, is canonically isomorphic to the singular homology of BGLR, and it is isomorphic to the group homology of GLR. So of course, if you take as definition of the group homology this, it is tautological. But if you use, let's say, the intrinsic construction for group homology, well, then you have something to prove here, but it is a general result not specific to GLR. So you have the Hurewicz map between homotopy and homology, which gives you an interesting map to GLR. And as it was discussed during the session of Peter, so now you can use this stabilization map because functorially you will get maps from Hn of some GLI of R to the Hn of GLR. And you can expect to be able to descend to elements from the homology of GLI for I, let's say, large enough. Because what will happen is that you will always have a stabilization isomorphism, meaning that for I large enough, Hn GLI will be isomorphic to Hn GLR. This is true also for SL, and you have many groups which have such stabilization properties. Interesting because you are then you can maybe expect to perform some explicit computation. Okay. So what we know, this is again a general result on the map, is, let's say, more or less, I mean, the kernel of the Hurewicz map is killed by factorial n-1. So we have something a little bit more precise in terms of torsion. But here, I mean, this is good enough, and you will see several times this torsion appear in the lecture. And even if we can be a little bit more precise and refine it, we are not necessarily that much lower than factorial n-1. And this is a rough bound, meaning that when we are able to compute very explicitly the kernel of the Hurewicz map, we found out that most of the time we are way below this bound. Sorry. Very well. So we gave a first connection between K-theory and homology of linear groups. Let's give a second connection, and this time with another object that introduced Peter and Jennifer in the past lectures. So as I said, so you have a filtering of the Q category by the rank, by modules of rank up to n. So from a point of view, this is very interesting because then each time you have a filtration, you have a long exact sequence. And if you have a family of long exact sequence, which are functorial, then it means that you have a spectral sequence. So this is very interesting. So this is the first time that I mentioned it, but next time I will mention it as spectral sequence. And so you have this long exact sequence, which, okay, this is just a byproduct of the filtration. But what Killen shown in the same reference is that the homology of the pair is isomorphic with some shifting to the homology of the linear groups with coefficients in the Steinberg modules, which was explained yesterday. And we also have this result, which is due to Quillen. And so if you, well, and here maybe it's a little bit, so it's here that there is the funny thing. Of course, you also have an Hurewicz map. So here, for simplicity, I take Z, but I mean, you have the same map for number fields, I mean, number rings. And this map, of course, is not exactly the one that we have seen on the previous slide. Okay? Yeah, of course.
When capital N is equal to 1, let's say R is equal to Z, what is Q1 of Z?
Z mod 2? The inversible element of Z.
Okay, so it's
yeah.
We defined, in the previous lectures, we defined the Steinberg module for a field, and we studied. I mean, we were interested into the homology of an arithmetic group with coefficient in the Steinberg module of the field. So here it's not the same thing because we have the homology of JLN of R with coefficient in the Steinberg module of the ring.
Yes.
So
yeah.
So it's not really related to the relations with it.
No, it's the same thing.
Steinberg of the ring is literally Steinberg of the field function.
Yeah.
That's literally the same.
Oh, okay.
Yeah.
So the Steinberg
Yeah.
on the right hand side is
Yeah.
the same thing.
Yeah. It's of course a good question, but the question for once is not misleading.
I also have a question. What is the I in HI of EQ1?
Well, it's I is it's any I, but maybe any I at least greater than 1, greater or equal to 1, I think. So yeah, at some point, I mean, you have a thing. I just, well, I'm sure that we use it in general, so very confident, but I just hope that there is not a deep result behind it. So, okay. Yes.
Q and R is a category.
Yes. No. Q.
So what is, when N is 1 and R is Z, you said that's a Z mod 2. Is that Z mod 2? Is that a
Yeah, there. What do you mean? The K1Z. You were speaking of K1Z.
Q1Z.
Ah, I have no idea. Okay, no. No. Sorry. Sorry, I thought K1. No. Q. I absolutely. I don't know. I never. Okay, that's a very good point. I never thought about it. Okay, black box. Just yeah. That's. I mean, you can think about it. So, but for this, I mean, you need to look really at the Q construction. I will be prudent with the KN. I mean, it's here. What we really need is just to have it as a filtration, okay, as a topological filtration. So at the categorical level, I will be more cautious. Okay. And in particular, I mean, you likely won't have the same nice properties than Q here. Because Q, I mean, the Quillen category has a nice property. It's almost like an abelian category. It's not what we call an exact category, and this was the purpose of the Quillen construction. And this is the key property. I do not, I do not have this in mind, but I do not claim that you have the same property for Qn. Okay. So here, you use it only in a more or less topological setting. And quickly, okay, so you have this guy, okay, and you know that it is isomorphic to this guy. So in somehow you can say that this guy is an object a little bit mysterious by itself, but for once it is isomorphic to an object that we understand better and that we are able to compute more explicitly. Okay, so it is not an isomorphism between an object that we don't know anything and isomorphic to another object which is as mysterious than the other one. So here, benefit between this object and this object. So in some, again, in some specific setting, you could be able to manage this part. But in the general setting, it is easier to manage this guy. And it's what we will show, and it's already what Jenny and Peter are going to show. I'm correct?
Yeah, absolutely. Or, I mean, present, let's say. But I have another question. So the spectral sequence really computes the homology of
BQ.
Of BQ, and now on the previous slide you said that K theory, in some sense, as a space maybe, is the loops of BQ. Why does the homology of loops of BQ help you to compute the homotopy groups of loops of BQ, whereas, I mean, the homology of BGL plus is just the group homology, and that does not help you to compute the homotopy groups of that space.
Yeah.
I don't know. I don't
So,
know the answer.
yeah. So, I'm going to answer this question. So, now, suppose that we want to compute either the full K-theory, or at least to understand better its p-torsion part, for instance, or even dream to be able to construct explicitly an element in it. Okay. So easier part, detect p-torsion. Less easier, well, easier, which is already hard. Less easier to compute the full group, and even harder to give explicit elements. Suppose that you are interested in doing that. So here, the hidden spectral sequence behind this filtration will give you a recipe for computing this guy for some m. Now, what I forgot to mention is that, again, thanks to the numerous results from Quillen, we have stabilization for BQ, so meaning that here we can downgrade to HM plus 1 to BQM plus 1. This is always true. So it means that you do not need to consider all the pieces of the filtration, only the wise one. So, but here again, as I said earlier, you have the kernel of the Hurwitz map, which is still a little bit mysterious. So you have this the torsion bonds that I gave on the previous slide applies here also, okay? Because we have the same property. I mean, I can give you a very explicit bond, but unfortunately, again, this bond is too lousy if you want to be very precise on, say, 2 torsion, 3 torsion, 5 torsion. Okay. And here, I mean, you need to find another machinery in order to deal with the kernel of the Hurewicz map. So you have a machinery in order to compute this part, because you have all the long exact sequence, which hidden, I mean, you can reformulate it if you want as a spectral sequence, which converts through that, and the piece by those guys. So if you are able, well, to compute all those homology of GLN or SLN or whatever, two coefficients with coefficients in the Steinberg groups, then you should be able, if you are lucky enough, to describe those guys. Why I'm saying if you are lucky enough? Because, well, you have maps here, you have differential of the spectral sequence. And I do not claim that it is easy to control those differentials. So, so if you are lucky, in particular, if almost everything is 0 except the last one, for instance, things like that. Yeah, I will show you some explicit example in the tomorrow lectures. But this is doable, okay? And you need to have another piece of machinery in order to control the kernel of the Hurewicz map. We do have at least a strategy which works in several cases. But there are no guarantees that the strategy will work every time. So far, we are lucky enough. Okay. And one of the why we are what we could expect in the torsion here, there is a part which is coming from the homotopy group of spheres. And why is that? Because, as I said earlier, we could also work with permutation groups. And I will have trouble to work okay. So we have a map. So we could stabilize it, and we end up, we could apply also the plus construction to let denote the colimit sigma, and so now I can take this, I can take the plus construction and look for the homotopy group of this guy. And in fact, it turns out that, let's say, the sphere spectrum is related to this guy. And you can expect to detect such element coming from here in the kernel of the Hurewicz map. So it means that you need to find some way to deal with this part. And if you are lucky enough, the control of, let's say the part coming from the sphere spectrum is enough to be able to, let's say, to detect very precisely the kernel. But you cannot expect that if M is large enough. Even okay. Now, let's connect the second player, but this is just, again, speaking of what...
Because on the left-hand side, you have a group, and on the left-hand side, you have a group.
Yes.
Defining sigma on the right, and then he wanted to add some notions.
Yes. Okay. So I was a little bit fast because I didn't want to erase, right? Okay. Okay, so you can, I mean, just you have one step. So the first step is you build the stabilization of sigma. So you get the equivalent of GLR for permutations. Then you look at the classifying space. You take the plus construction. You take the homotopy group. So you get something. And what I'm just saying is that this is very close to homotopy group or sphere. And several parts of this is in the kernel of the Eurovich map. But it is again, it's also a trickier part. So of course, if you want to detect only very high torsion, or if you are only interested in the rational part, then of course, I mean, you can ignore this, because rationally, or if you are killing enough torsion, this bed in this one. And so you no longer need to care about the Eurovich map. So it depends really what you want to know very precisely. Okay, so again, just a few words about Borel-cell duality. So it's again to just to glue things together, but already Peter and Jenny has mentioned it in more details, except that here I give you a little bit more explicitly the long exact sequence, which involves the cohomology of more or less the arithmetic group. So here, SLNZ, GLNZ, or your favorite one. And how it relates to the homology of gamma with coefficient to Steinberg. And in the middle, you have an obstruction. And the obstruction is so-called the Farrell cohomology of gamma. And mainly it is torsion. And when we work rationally, or at least when we are willing to kill all the p torsion up to n+1, then we get this isomorphism. And you can forget about the Farrell cohomology. But nevertheless, if you are interested to detect all the pieces of the torsion, then you have to compute the Farrell cohomology. Again, in somehow you have a hidden spectral sequence behind it. And you can really get the full cohomology with coefficient in the orientation module. And here you have to be very careful because you have an action which is given the Borel-Serre machinery. And the action is not necessarily trivial. In fact, most of the time it is not. But in our setting, we can recover the cohomology with trivial action. Okay, that's using this.
What is S? N+1?
Sorry. Oh yeah. Sorry. Thank you. This is something that I should have defined earlier. So Sn+1 is what we call the Serre class. So it means that we work modulo p group, p torsion. Let's have it very simple. We work modulo p torsion for prime p, which are less than n+1. Okay. So meaning that suppose that you have a group G plus some group G prime, which is p torsion, and a group H plus H prime, which are p torsion. And suppose that G is isomorphic to H prime, to H, but not the p torsion part. If you work modulo Sn+1, you get an isomorphism, sorry. So this is a nice way to deal with p torsions, and for p torsion less than some bound. So if you want from an algebraic point of view, it's the same way. I mean, if it's the same than tensouring by Z 1 over P, 1 over P1, 1 over P2, and so on for all P, for all Pi less than n plus 1. More or less the same. So of course, if you work rationally, you do not care again to have this.
So what is involved in the action on the orientation of is that algebraic?
No, it's geometry. I mean, it's coming from the geometry. Yeah. That's. Okay. Okay. So now that we have connected, let's say, K-theory with homology of GL with coefficient to Steinberg, and we have connected it also with the cohomology of GL, and also with the homology of GL, with the plus construction. So now we want to connect K-theory with some number theoretic problems, and to see how we can use it either to apply it for number theory, or the other way around, to use number theory to help understand what types of elements we could find in the K-theory. And also elements that we could find in the homology or the cohomology of GLN. Because here, sorry, I'm back a few slides, something that I forgot to say, that suppose that if you have elements from K-theory, which are, of course, in the case of the Hurewicz map, so you will detect them here, okay? And it means that you will detect them here, and at the end, you will detect them also in the cohomology of GL. So it meaning that if you expect some elements of high torsion in the K-theory, this element should come at some point from the cohomology of GLN for some, or SLN, or some arithmetic groups. Okay, back to okay. So we have a way to relate a special value of function in general, so in particular for zeta function, to the torsion part of the K theory. And in particular, it was shown by Soulet in the late 70s, that denominator and numerators of zeta 1 minus n divides, respectively, either the cardinality of the torsion part, of course, of k2n minus 1 of z, or, and similarly, the cardinality of the torsion part of 2n minus 2 z. And the result extends to number rings, by the way. So it means, so it gives you a recipe to know what type of torsion you could expect within the K group of Z. So for instance, this is a very easy exercise. Well, for instance, you take zeta minus 11. So it is this, okay, the famous 691 from the Bernoulli number. And so it means, according to Soule, that there exists an element of order 691 in K22 of Z. Okay. And now exercise for this for the next session. Give explicitly this element. Okay, that's very difficult. So, as on the other hand, we know that we have some, let's say, generic torsion, which are coming from the finite subgroup of arithmetic groups in general. So GLM of Z, SLN of Z, but or GLM of some number rings and so on. So you can really have two worlds, you know. I mean, you have the worlds of, let's say, a generic torsion, a generic P torsion, that you know that likely this P torsion will happen. But this P torsion will be bounded. It will be bounded by the order, if you prefer, of the finite subgroup arithmetic group. Then some high torsion element. You know that they exist for some M, but you don't know exactly when they appear, and for which M they appear. This is a difference. And then you have the rational part that you can compute with sometimes other tools.
That 22? Yeah, 22.
No, it's 22.
What's N there? N in your example? It's 12, is it?
Yes.
So 2 12 is 24 minus 1.
But
4, right?
Yeah.
24 minus 2 is 23.
Oh, so sorry.
Thanks.
Question.
Yes.
This element of order 691, can you do you know it explicitly or?
No.
No, this is the result of my question about the result of 3. Is it an explicit construction? Or?
No.
Okay.
No. That's exactly. No. It was a joke when I say exercise. Find it. I mean, we tried to find it since 1979, and we still do not have it, unfortunately. So we have educated guess where it should come from, but well, it's yeah. So it's a type of result where you know that something exists. You are very precise about the property of what exists, but you are unable to build it explicitly. Okay. So let's. Ooh. Whoa. Wow. Oh, sorry. Okay, so am I correct assuming I have 5 minutes?
Yeah.
Okay. Very well. So my other favorite example is the Kummer-Van Diver conjecture. So Kummer. So we could, of course, phrase it in very simple words. So let's try to phrase it in maybe the less simple word. So if, I mean, you know that what in the conjecture is that if you look at the class number of the, let's say, part of the cyclotome field QZP, then this class number is not divisible by P. So a way to phrase it in simple words from using, let's say, the class group, it means that somehow, I mean, the real part, if you want, is equal to 0. So what was found out in the 90s by, so in fact, independently by Kurihara and Soule, is that we can connect the Kummer-Van Diver conjecture to some pieces of the K-theory of Z. More explicitly, so if all the group Kn, when K for n Z are 0 for all n strictly positive, then it implies that this part is 0, so meaning that the Kummer-Van Diver conjecture is true. And this was also a supplementary motivation in order to compute those groups. And of course, which are still unknown, and the Kummer-Van Diver is still unknown. So I will give you something a little bit more precise about what is known and what is not somehow, but likely in the second talk. Okay. And yeah, so let's. This is very annoying. Yeah, so I prefer to stop there because I have rather technical slides in the following. So I will try to explain a little bit how it works, this relationship, in the next lecture. But quickly, you will be able to look at the slides for more details. And then I will speak, I will try to realize other points from the cohomology of groups to number theory, and introducing a tool which is called the earlier characteristic of a group, and which is also a very interesting tool for us, in particular, in order to check that our data are, let's say, correctly computed. Okay, so I will stop on the 11th slide. Wow.